So we have looked at lots of different aspects of capacitors, how long it takes to charge them and discharge them, and the exponential aspects of that. And we've just looked at how we can combine them in series and in parallel. The last little thing that I want to talk about capacitors today is how much energy is stored in them, because what we tend to use capacitors for a lot is to charge them up, and then we allow them to suddenly discharge and release that energy that's stored inside them. For instance, a flash on a camera. If you want a powerful flash, you might have a capacitor in there rather than a battery, and you would charge the capacitor up. And then when the capacitor is fully charged, it will suddenly discharge very, very quickly and release the energy stored in it as the flash of light. That's sometimes why you have to then wait for the flash to recharge, because the capacitor is charging up. Okay, so this isn't going to take us very long, and it's going to repeat some similar things to what we did when we looked at the energy stored in a stretch spring, for instance. So it'll be a little bit of recap of that. So this isn't going to take us very long, but here are the notes on this board, and I'll make my way through it with you. So we need the energy stored in a capacitor, and whenever we're talking about capacitors, our go-to equation is Q equals CV. And what we're just going to do is have a look at drawing the graph of that. Traditionally, the graph is always drawn with V on the y-axis. And the subject of the equation is currently Q, so it will make our lives a little bit easier if we just rearrange this equation to see that it's equal to V is 1 over C times Q. And we just compare this with y equals mx. And we can see that if we put V on the y-axis and Q on the x-axis, then we're going to get a straight line through the origin, and its gradient is going to be 1 over C. So the question is, well, why have we chosen to draw a graph of V against Q? So does anybody remember any equations involving energy, V, and Q from year 12 electricity? If you do, feel free to shout it out or put it on the chat.
V equals E over Q.
V equals E over Q, yeah, which is more usually written like this. So W rather than E, because it refers to the work done in charging the capacitor. So if you think that the two plates of the capacitor are initially neutral, and then we maybe add 1 electron to one of the plates, and that causes the plate it came from to become positive. Remember, the electron hasn't jumped across the plate, it's gone all the way around the circuit to the power pack, but the effect is that it's jumped across the plate. Well, moving 1 electron means that there is just 1 lot of attraction pulling it backwards, and there was no repulsion to place it onto a neutral plate. So it didn't really take very much work to move the electron from one plate to the other. But then when we add the second electron, we're now adding an electron to a negative plate, meaning that there was a little bit more repulsion, and we were pulling it from a doubly positive other plate. So it just took a little bit of extra work to move the second electron compared to the work it took to move the first electron. When we then move a third electron, we're now trying to push an electron onto a doubly negative plate. So there's twice, 3 times the amount of repulsion pushing it back. And we're trying to pull it off a triply positive other plate. So there's more force pulling it back again, more force required to push it on against the repulsion. you can see that with every successive electron that we add, there is more and more and more energy required. More work needs to be done. The distance is the same between the two plates, but the force is getting bigger and bigger and bigger each time. And like I said, it doesn't matter that the electron is actually traveling around an external circuit via a power pack. The effect is to have moved an electron from this plate to this plate. And so the effect is exactly the same as moving an electron across this gap. So it would be the force times the distance moved across this gap. We're going to go on to a topic about the electric force after this one, and we will return to that calculation and you'll see exactly how it's done. But for now, you can see in principle that for every electron that we add to the negative plate, it takes more and more and more effort to do so because the force is bigger each time. And that's what this graph is showing us. This graph over here has V on one axis and Q on the other axis. And what we're saying is that if we multiply the two together, we will get the energy required to complete the change. So if the plate has a certain amount of charge on it, and then we add a tiny little bit of extra charge to it, then what the formula is telling us is that Q times V will be the work done but the formula does assume that V is constant during that change. So we just need to make it a very, very small amount of charge that we add so that this rectangle really is a rectangle and not a trapezium. This tiny little bit on the top, that tiny little triangle right on the very top of that rectangle there, we are free to ignore that as long as delta Q is very, very small. And we've played this game many times before in all different topics, that we can make delta Q infinitesimally small, meaning we can make it as small as we want to, meaning that we can consider V to be constant during that very small change. We then ask, well, how much energy is stored in the capacitor in total? Well, if it is storing this much charge, then what we will have done is added up slice after slice after slice after slice after slice after slice after slice, all the way until we eventually get to the idea that the area underneath this straight line graph is the energy stored in the capacitor. And the area of that triangle is therefore W is equal to the half base times height. And that's our formula for the energy stored in a capacitor. If we substitute from Q equals CV, we can get slightly different versions of this equation. So if you happen to have the capacitance and the potential difference, the final potential difference, you might prefer that version of it. And if you have the charge stored and the capacitance, you might prefer that version of it. So common applications of this would be to take a capacitance of a capacitor of known capacitance, raise it up to a known potential difference by attaching it to a power pack and waiting for it to charge. And then if you apply this formula, this is the most commonly used version of it because we generally know the capacitance and the potential difference more than we do the charge. And so that would give you a value in joules of the amount of energy stored on the capacitor. And then you could discharge your capacitor through a bulb, say, and it would allow you to work out how much energy will be released from the bulb as heat and light during the flash, during the discharge. So that's your last little set of work on the capacitor. Really this topic hasn't been teaching you about the capacitor as such, but more about the physics surrounding the device, the idea that we can end up with an exponential growth or decay and mathematically model that we can use this formula the way we used to use V equals IR to replicate the derivation of the combinations in series and parallel as a way of reinforcing what you did for resistors in series and parallel, that we can do this. And it's really reinforcing what we did on springs. You remember that the formula we came up with for springs was a half Fx or a half Kx squared. And really to give you an idea of the holistic nature of physics, the way that the same ideas and the same mathematics keeps cropping up again and again and again. So the energy stored in a capacitor is similar to the energy stored in a spring. The combinations of capacitors is similar to the combination of resistors. The rate at which capacitors charge and discharge is similar to the rate at which radioactive substances decay. We still need to come on and remind ourselves about that from GCSE. We haven't done that topic at A level yet. So the capacitors topic really is more a vehicle to learn about the interconnectedness of physics rather than learning about capacitors in their own right. But if you're an electronics student, you now know a little bit more about capacitors from a physics perspective that you can couple together with what you know from electronics. Okay, that's all that I want to do with you today, actually. So I'm going to leave you with some work to do. So here is some work for you to do. So the little bit that I've just done with you on energy is on a short little chapter in the book, 21.3. I just need you to skim read through that and do the 5 questions. It won't take you very long, 10 minutes at most. Then at the end of this chapter, there is kind of some wider reading. It's not particularly examinable. It's just for information. 21.6 just talks you through some places in the world where you might find capacitors and where their applications might be. It's kind of building a bridge between the physics and the electronics. So have a read through that, but don't worry too much about 21.6. Like I say, it's not particularly examinable. And then at the end of the chapter, there are 4 past paper questions. And I reckon you can have a good go at those during what remains of this lesson after you've done 21.3. But if not, it's some private study for you to do during the week.